So hello everyone, welcome back to another particular lecture of our reagent chemistry course, and this is class 32, and in this particular class we will mainly focus on the reagents which actually used to transform ketone to the alpha beta unsaturated ketone. That means imagine that this is your ketone compound and you want to transform this ketone to an alpha beta unsaturated ketone. That means you want to generate a unsaturation here. So what is the reagent? That will be discussed in this particular class. So basically there are two different type of reagent is there. One is the Segusa oxidation and another one is the Selenation. So we'll discuss both. So first let us talk about the Segusa oxidation. Okay, Segusa oxidation, it is a two-step method to develop ketone to their corresponding alpha beta unsaturated ketone. And what is the reagent of this particular oxidation reaction? That is TMS chloride, base and palladium. Now, if you see the reaction mechanism that we will discuss in the next slide, you will find that palladium 2 might be used in the stoichiometric amount. But the palladium 2 is very costly as well as it is a metal. So, generally we tend to use this palladium 2 as a catalytic amount. So, the scientists introduced some kind of terminal oxidant like oxygen, parabenzoquinone. This type of terminal oxidant has been used in the previous lectures where the OSO4 has been used, process dihydroxylation. There also NMO used as a terminal oxidation. Similarly here, this palladium, if you use the palladium at a catalytic amount, we have to introduce some kind of terminal oxidant, because this particular reaction process, palladium 2, it goes to palladium 0, which is the active catalyst, which again return to the palladium 2. So do this particular transformation or to this type of catalytic cycle, we need some kind of terminal oxidant which can be used in a stoichiometric amount so that the palladium become the catalytic one. So here also that oxygen, parabenzoquinone, this type of terminal oxidant has been used, and this is very cheap compared to palladium. Okay. So let us see one example of Segusa oxidation, and then we'll move to the mechanistic pathway. Okay, so here you can find this is your carbonyl compound, this is ketone, where this is the alpha position and this is the beta position. Similarly, this one is the alpha position, this one is the beta position, but this is little hindered over this is position. So always remember that this Segusa oxidation or selenium oxidation, they are tend to form alpha beta unsaturation where there is a less sterical hinder is observed. Okay, so here you can find that TMS chloride, that is one of the reagent, and base here lithium TMP has been used as a base, and the second step is the palladium 2 has been used in presence of acetonitrile solution to get our this type of compound. There is the alpha beta unsaturated ketone. Okay, now let us move to the mechanistic pathway. So this particular mechanism is involving, first is the silyl ether formation, and the second time is treatment with palladium 2, which actually nothing but a beta hydride elimination. So let us see the particular mechanism. So this is the step 1. This is the step 1 where basically this particular carbonyl compound has been treated with the TMSCl and base to form silyl ether. How it is forming? You can see here, this is the alpha position which contains H, which is the acidic hydrogen. So base will capture this particular acidic hydrogen, and then a negative charge is formed here. Okay. Now this negative charge will go here, this will go here. So here O negative is formed, which actually attack in the TMS to remove that chloride, that we got the silyl ether. Okay, now this particular silyl ether in presence of palladium, okay, that palladium chelate with this particular double bond, chelate with the palladium, and it will form this type of intermediate, and they are in equilibrium. So when this particular intermediate is formed, now you can find here, this is your palladium center, here the alpha, this is the beta, and this particular hydrogen present here, okay, this is the beta hydrogen. Now we know that palladium has the failed d orbital. So this particular d orbital actually attack the sigma star orbital of this particular hydrogen to get this type of beta hydride elimination, and thus we will get the corresponding desired product, that is the alpha beta unsaturated ketone compound. Okay, so now in the next segment we talk about the another reagent, that is a selenation. Selenation followed by oxidation followed by elimination. This is the main sequence of this particular reagent. Okay, the initial selenation of the particular carbonyl compound has been observed, followed by oxidation of selenium center and elimination. Here the reagent is pH acivia, that phenyl selenium bromide or phenyl selenium chloride. This can be used to selenate enolate of ketone, or ester, lactones, lactams, all are actually show this type of reactions. Okay, so let us see one example. As I already discussed in the previous segment, that mostly that particular alpha beta unsaturation has been observed in the lesser hindered site over this case. So we observe this is our starting material, and we observe this type of alpha beta unsaturated ketone. So why what is happening in between? Let us see. Initially that LDA THF will form enolate as expected, and that particular, in the case of enolate where the TMSCl, in presence of TMSCl, that oxygen center attacked in the particular TMS to form OTMS, but here that carbon center attack in the selenium to form the selenate enolates. So why it is happening, we will learn in the enolate chemistry part, enolate chemistry courses, because of the hard enolate, soft enolate concept is there. So we will discuss there, hard center, soft center. Okay, so remember that in this particular cases, although it is forming enolate, so the negative charge will actually attack here to remove the bromine to form this type of selenate enolate, and then this selenate enolate will first oxidation, and the second is the elimination takes place to form this type of alpha beta unsaturated ketone. Now let us see the actual mechanism of this particular reaction. And also common oxidants like hydrogen peroxide, ozone can be used to perform the syn elimination. Please remember that this is the syn elimination pathway has been followed. Now let us see the mechanistic pathway. Like initially, as I already discussed, that it will form enolate, then this particular enolate comes back and it will attack here, and bromine goes out to get our this particular selenate compound. Now in presence of oxidizing agent, like for example H2O2, this will actually oxidize the selenium center to form this type of product, which now undergo syn elimination pathway to form the corresponding alpha beta unsaturated carbonyl compound, and the byproduct is PHACOH. Okay, now let us go drift a little bit different step, where suppose you have a alkene, and now you want to form allylic alcohol. Now what should be the reagent there? The reagent is SiO2, that's selenium dioxide. That selenium dioxide can be used for oxidizing alkenes to their allylic alcohol. And terminal oxidant was used while using catalytic SiO2, that I already discussed in the previous segment. Okay, so what is the mechanism of this particular part? See, first a in reaction has been observed where this particular allylic hydrogen are actually captured by a ring concerted manner to form the allylic selenic acid. Okay, now if you see this particular intermediate closely, you can find that 1 1 2 2 3. That means here a 2 3 sigmatropic shift reaction has been observed here, where this particular bond breaks apart and this particular bond is forming. So after 2 3 sigmatropic shift, we got this compound, which in the water workup or quenching, we got our final allylic alcohol product and ACOH whole 2 as a byproduct. Now this ACOH whole 2 in presence of terminal oxidant, it will form ACO2, which again go to the reaction mixture and do that particular reaction. So this is the oxidation of alkenes to allylic alcohols. Now there is another interesting thing in presence of ACO2 type of reaction, but before that we will see what is written here. That mechanism involves in reaction followed by 2+3 cycloaddition or sigmatropic reagent, we can say, and also oxidation typically occurred in the more highly substituted terminus of the alkene. Now if you have a carbonyl compound, if we treat that type of carbonyl compound in presence of ACO2, it will show dicarbonyl compound, where that particular alpha carbon is getting oxidized. This is alpha carbon, this is alpha carbon. In presence of ACO2, this particular alpha carbon getting oxidized. Similarly, when we treat with acetone, this particular alpha carbon is getting oxidized to form this type of product. And similarly also this type of norborelin system, so the same thing has been observed. And also ACO2 oxidize the benzylic position also. That means if you treat toluene with ACO2, you will find a benzaldehyde. So with this we have to end this particular class. In this particular class we have learned about the Segusa oxidation, selenation and ACO2 based transformations. So in the last class, in the next class we talk about oxidative cleavage. So thank you for listening.